let me show you some effective theory.
Yeah, effective theory.
Okay. So now I want to raise some question. So apart from this nice RPath experiments that people did, so are there any topological experimental signatures? Right. So can I do some yes or no experiment? So if the experimental result is yes, I know it is a topological insulator. If the experimental result is no, I know it's not. Can I find such a experiment? So of course there are many proposals. So over here, I try to point out that we find an anomalous Drossman effect on the surface superconductivity of the topological insulator. This can be used as a topological signature, experimental signature, to detect these states. Okay, so to show you how this effect show up in this topological band structure, let me firstly give you some intuitive picture of why I can realize a single Dirac cone on the surface of a 3D system. So let's start from this 2D limit, right? So in the 2D limit, I can certainly have 2 Dirac cones, like one half of graphene. So in the presence of terms of this spiral coupling, this is allowed. So then I want to stack all these layers in the 3D system. Then I introduce interlayer couplings. But the trick is, over here I want to couple this node to the other node in the second layer, and so on and so forth. So only when I couple 2 nodes, they can open up a mass gap and become insulating. But if you keep doing that, you can find there's a way to connect all these Dirac nodes such that there's one guy left on the surface, top surface, another guy left on the bottom surface. And all other Dirac nodes get out. So this is the sort of most, I feel is the most simple way to visualize how it will space.
I missed why are there 2 Dirac nodes?
Yeah, so you imagine you have some lattice model in 2-dimensional system, which have 2 Dirac nodes. This is allowed in the process of campus symmetry. Yeah, I just want to show why in 2D it's not allowed, but in 3D it's allowed to have a single Dirac cone on the surface. So this is how you visualize that. This single Dirac node has many physical consequences. First, for example, it's stable to a non-magnetic disorder. So there's no localization. So this is different from the Euro-symplectic class metal, where you have terminal symmetry. Or this, for example, like graphene, if you put in non-magnetic disorder strong enough, you still get it weak localization. But over here, the claim is no matter how strong the disorder put in, you don't localize it unless you break terminal symmetry spontaneously. If you apply magnetic field, there's also a striking effect, which is this half-integer Hall conductance. And if you suppose I coat this surface by a superconducting layer, what people can show is this superconductivity on the surface is actually very non-trivial. It's very striking. In the sense that if I create a vortex on this surface, what people show is there's actually a Majorana bound state inside the vortex core. So in general, these two ways are the only 2 ways to make the surface.
So how thick is your superconducting layer? I mean,
okay, so you don't have to be you don't even have to have a whole surface, because the surface itself, before you put in superconductor, is a metal. So you can simply put the superconductor somewhere else, but close, to induce a proximity effect. You know what I'm saying? So if I have a superconductor in contact with the metal,
I know that,
the outer parameter is going to penetrate in some power law.
But how can you induce Majorana states in the vortex core? Is it what you're saying, or?
No, I thought you were saying, do I need some special thickness
No, you said that you have Majorana states in the vortex.
Right.
What you said.
Right.
So, but it can't extend all the way if the superconducting layer is very thick. Let's say I have 1 centimeter thick layer.
Yeah, the point is.
So how
when
far
this
does it extend?
Yeah. So the claim is there's a 1-0 energy state.
Right. Is it the localized surface state?
Localized on this surface,
Ah,
on this
okay.
on the interface between the superconductor and so because we're serious, we probably all know this Majorana fermion, but it's still good to just to give a quick picture why Majorana fermion is realized in this surface superconductor. Because we know that in the vortex of a P per IP superconductor, there is a Majorana mode. This is pointed out pretty a long time ago. But then what these people, Fu and Ken, realize is the surface superconductor in a topological insulator is very similar to a P per superconductor. Spin is to be P per superconductor. Although you have a temporal symmetry. So the way to visualize it is you write down some effective theory. You find that the spin on the surface actually wind around if I go around this direction. So there's an intrinsic coupling between the spin direction and the momentum direction. So this is exactly the spin of the coupling. So then you put in some S-wave superconductor. So you imagine you put just an S-wave superconductor close by and induce a proximity effect. So in this local electron basis, it looks like an S-wave. But if I translate into this band basis, into this Engel state basis, you find there's a winding number around the Fermi surface. So it's the same thing as a P-per superconductor. So this is how you visualize it.
The psi k's are eigenstates of the non-interacting part. The first part, the Dirac part.
Exactly. At finite. At the Fermi level.
But it preserves time relative there.
Yeah, it preserves time relative invariance. So that means when you do this basis transformation, you were sort of you are not breaking temporal symmetry, but you have this winding number. So this wave function, they all bound.
So I really want to ask this question, but maybe it goes beyond the talk, which is in the classification table of topological insulators. Where does it belong to?
What was your question?
What is the classification table of topological insulators? So this is not a pure superconductor because it breaks time relative invariance, but it's not the usual topological insulator because it has a superconductor-like term. So, but it has to be something else. So what is that?
Yeah, I agree. Yeah. So, but there's an issue, right? So so let me firstly restate the problem. So the problem is there's a full table of classification of topological superconductor and topological insulator. And this guy, this surface superconductor, is not within that classification. That's the question. But you still have this weird this vortex physics, which is similar to a topological superconductor. So my answer to this question is the following. So there's an issue. So can I smoothly tune this surface superconductor to a can I smoothly tune this surface superconductor to a regular superconductor, 2D regular superconductor without a phase transition? So you'll see there's some weird vortex mode, right? There's some weird vortex mode bound state inside vortex core, but that not guarantee you to have a phase transition between this phase and the regular surface superconductor. So what can happen is this vortex Majorana mode can have some phase transition. So when you tune the parameter from following me. So if you tune the parameter from this topological insulator to a surface superconductor to a regular insulator surface superconductor, I try to say there can be no phase transition. But you can ask, how does Marangoni disappear? Right. Over here I have a Marangoni, over here I don't. And what happened is when I tune these parameters, at some point there's some the vortex, suppose there's a vortex line. So Marangoni here and here can come over. But it's only happened along this vortex line. It's not in the bulk.
But this vortex state breaks time reversal.
Yeah, because you have vortex.
It seems like, huh? Well, you created a vortex, right? It spins in one direction, but not current circulate in one direction, but not the other.
Also, would you call this S wave or S plus V wave?
Indicator also.
I think it's a matter of just checking signatures.
I would rather call it S wave because it's a don't break time reversal.
This is only happening at one point. It's not a film that you make.
And
But you could write this constraint as
and it's a symbolism.
symmetrical.
No, I don't. I don't think so. I think there's a difference. So,
I mean, S wave you would also have a combination of up at minus k and down at plus k.
yeah, I know.
Typical S
I know.
I mean, it should come out different when you write down your.
Yeah, so let me answer this question. So maybe, so at least in the presence of reflection symmetry, I think there's a difference.
Yeah.
So this a two-state dimension has a difference in reflection. Yeah. But anyway, so this is the only pairing on the surface which can open up a full energy gap. So there's no other pairings that can open up full energy gap. Okay, so I want to focus on this superconductivity on the surface because, as I mentioned, I will propose a Josephson effect on the surface. So naively, this vortex physics, this non-trivial part of this surface superconductor is about this 2D system. But if you think about it more carefully, it's actually coming from a 3D system. Because if there is no such topological insulator bulk, you don't have that from the vortex core. So that tells you that the topological nature of this surface superconductor is actually from the 3D system. So this motivated me to introduce a 3D way to describe the low energy physics of this topological surface superconductor.
Can I ask an educational question? Because I'm not familiar with this topic. So what's the statement, basically what's this experimental, just Gedanken experimental setup? You just cover your insulator with a layer of superconductor and automatically get a vortex?
No. You put in a vortex.
Oh, you put a vortex by hand and only then you see a
sure.
Oh, I see.
Okay. So what is this 3D way? Actually, there's a very elegant model that you can write down for this 3D topological insulator. So this is just a simple Dirac model. So what you have is a 4-component Dirac equation in the 3D system. And then you want to open up a mass gap to this 4-component Dirac home. And this, you can find that there's only one mass you can write down, which preserve terminal symmetry. Of course, I need some realization of this Dirac equation. I should know what terminal symmetry means in this theory. But after I know that, I can show that there's only one mass term which preserve terminal symmetry. So you can show that depending on the sign of this mass, is it positive or negative, you are either in this topological insulator or in the trivial insulator. So this is the simplest effective model of a bulk topological insulator. So you can sort of visualize in a bulk topological insulator. In the bulk, this NZ is negative. In the vacuum, this is a positive. And on the surface, you exactly have this changing sign of NZ. So you have this gapless mode. This is a single Dirac home on the surface. So what about superconductivity? So in this effective model, the superconductivity you can also very compactly written down as some masses. But now it's a superconductor, so it's in this Majorana basis. So it's a basis of pairing, and this pairing you can show there's only one pairing which don't break chiral symmetry and open up a gap. So this pairing is exactly this isolated pairing of this surface superconductor.
Can you see that beta 5, how is it related to beta? I thought it
Oh,
was
just a
only-
beta. Just
oh, it's a product of all the alphas
yeah,
and beta, right?
yeah. Just there's this 5 anti-commuting
Right, so
matrices.
it's basically a product of those
Right,
4, right?
right, right,
Yeah. It's like gamma 5 and...
right. Okay. So, yeah. So what you can show is this superconducting gap is collaborating with this topological insulator gap. So meaning, if I have both gaps, superconducting gap and topological insulator gap, they add up. They don't cancel. So meaning this gap, in this effective theory, they are corresponding to anti-commuting matrices.
So is the symmetry of the gap important for you?
Yeah.
So what kind of symmetry are you seeing?
That's
Oh,
what-
Yes.
tensor symmetry.
No, S, D,
That's S.
Yes.
S. Right, that's what
Yeah. So this is the S. Okay. So in fact, in this effective this Dirac limit, in general, you can write down 2 different kind of pairings, S pairing and P pairing, and but this P pairing breaks chiral symmetry. So this is only so I try to say chiral symmetry itself tells you that there's only one pairing. Okay, so then if I introduce this 3 vector n by the real part and the imaginary part of this pairing, this isolated pairing, and this nz, this bulk topological gap, then of course the modulus of this vector will be the full gap. So in this n representation, so I can visualize this vortex in a 3D. So because the vortex, you can see over here in the bulk, this n vector is pointing down. And outside, this nz is a plus, and there's no superconductivity. So this n vector is pointing up. On the surface, you have vortex. So this nz is 0, but this real and imaginary part of this delta went around 2 pi. So that means this vortex in this n representation is exactly a hedgehog. So it looks like a hedgehog. So all this n around it is pointing outward.
So NZ is dynamical variable? Just texture.
You can visualize it as dynamic variable, but in the experiments not.
So is it precisely like the theta term that's rescaled and shifted precisely?
What is theta term that we're talking about?
You know, the topologically non-trivial insulator is theta equals pi and the vacuum theta equals 0, I guess.
So why that's related to what I'm talking about?
I mean, it seems like you were saying that nz equals -1 is topological insulator and nz equals +1 is vacuum. So
Right. But that's I think that's a completely different issue. So that's that the theta thing. This a theta electromagnetic response.
Okay, so that's implying that if you have a dynamic fluctuation of theta by some time symmetry breaking, it's not going to work. I mean, affect the kind of physics we're talking about right now.
Okay. So you are saying this nz is just theta? Is that what you're saying?
No,
But
I mean, like, you of course would have to rescale and shift it around to make it equal to what you're saying, but yeah,
Well,
basically. I mean,
I don't think
I'm
there's a-
asking, yeah.
I don't think there's a much physics about containing in your question. So it's probably some convention or some formulation. But what I'm trying to say here is there's a 3D way. There's a 3D way to visualize this vortex.
Can I ask you? So, where in here, or do you lose this information in continuum theory, a distinction between nz equal -1 or +1 being trivial and non-trivial? So, it seems like in the continuum theory, I can't tell what's trivial insulator, what's non-trivial insulator.
Yeah, that's true.
That's true,
That's
right?
true. That's true.
So I need some lattice
You need a
regularization to
regularization,
distinguish, because I need to know
So you need to know. So
the full band structure, right?
Exactly. So you need to know what is vacuum.
What is vacuum,
What is
exactly.
vacuum? So, yeah. So with a lattice model, you can tell because then you can put that into vacuum to see what the surface.
Well, but in
is.
particular, I need the full block states to compute, for example, whether
Right.
they
Right. Exactly.
some winding.
Exactly.
Here I cannot.
Here you
It's
cannot.
only near the point.
Here you cannot.
So let me ask you one more thing. So this pairing potential doesn't contain any kinetic energy of currents which circulate on the borders. So are those?
Oh, so I didn't write down the kinetic part of this order parameter.
So is there any influence of this circulating currents on the states you're talking about?
No. So my answer is this. So there's a zero energy bound state
In the
that's
core. In the core.
and that's not affected by the circulating current.
Well,
so
the
that's
circulating
included
current
there.
actually produce the core,
Yeah, that's true. So
So-
it's included there.
but there is no back effect of the circulating currents on the state below superconducting layer.
Okay, so let me answer the question this way. So the thermal current, of course, break thermal symmetry, and of course it's gonna induce some current close by, even in the metal. Sorry,
Yeah,
in the surface states.
in the surface states.
Right. So that's the only effect.
And what effect?
That is the only effect.
Right. But
So-
is there any energy shifts because of that? Because that will
Energy
be
of what?
of the levels.
The zero energy level cannot shift.
Oh,
It's pinned there. It's a topological feature. So it's a
But somehow, once you break time reversal, the topological structure somehow isn't the topological insulator very strongly relies on not breaking time reversal invariant? You know, it's time reversal invariant topological insulator.
let's say it again, sir.
The property of a topological insulator, even in the bulk, very much relies on that it's a time reversal
Right,
invariant topological insulator.
right.
But now in the around the vortex or near the vortex, this is not the case. You now explicitly break the
That's
time
true.
reversal symmetry.
That's true.
So maybe that's related. You know, the same
Yeah, I'm
question.
trying to
Is there any
understand,
implications
yeah.
for kind of the general, you know, what is the property of a topological insulator, even if you locally break time reversal symmetry, which is what this seems to be doing. I mean, thermodynamically it has to be the same because it's only.
Okay, so I try to say that the defect physics is a probing of the phase,
Right.
but it's not a
Doesn't change the bulk.
doesn't try to change the bulk of the phase.
Right.
Yeah. So
Well-
in fact, to realize a Maillard fermion, you certainly need a time reversal breaking. Otherwise, you have Fermi degeneracy. You have two Maillard modes.
So
you need that.
in other words, you're saying that if I just apply a current which flows along the superconductor, let's say, just
Mhm.
induce it, my zero energy state will still survive,
Yeah, yeah,
even in the presence of current.
that's true. That's true. Yeah. So in a superconductor, this energy level, because it's just particle hole symmetry, so you always have a positive and negative energy levels, and there are two of them, right? It's a pair. But it's a weird thing about Maillard mode is it's a single one, so it's C equals C dagger. So that's not tunable. It's required to be at the zero energy.
Somehow.
It's
But
actually-
somehow it's required if there was no time reversal. But once there's no time reversal breaking. But if in the region where it is time reversal breaking, where this vortex is, there's no protection anymore.
No, there's a protection. It's protected by far away. So this has happened in the general topological band structure. The defect physics, this bound state, is protected by far away, by this global. This is global protection. Okay. So now, with this this defect physics in mind, so in fact we try to think about a smooth texture. So are there smooth textures of this N configuration? So by smooth texture, I mean this N is non-zero everywhere. It's a smooth configuration. And are there some signature of this band topology, and are there topologically distinct solitons? So in fact, people know that there is this solitons because so what is the smooth configuration N means at every point in the space it mapped to a point on a two-sphere because it's N. I can normalize it because it's non-zero, so it will be a point on the two-sphere. So this texture is characterized by this mapping from a 3-space to a 2-sphere. And I can compactify this 3-space into S3 because far away I should be pointing to the same direction to have a finite energy system. Right. So this mapping have non-trivial index. So this is a so-called Hopf index. So if this is S2 to S2, I think then people are more familiar. It's just the Wanning number, the number of covering of this S2 to S2 mapping. But for S3 to S2 mapping is less obvious. So this was firstly worked out by Hopf, and he showed that this mapping is still labeled by an integer. So here I try to give you a visualization of this Hopf soliton. So this mapping can have many topological indices, can be -1, 0, 1. So what is this indices means? So what it means is, suppose I choose 2 points, arbitrary 2 points on S2 sphere. Because it's a 3D to 2D mapping, so there will be pre-images in the 3D space. Right? And this pre-image will be a 1D system, will be a loop, 1D loop. Right? So you map a loop to a point. That's how you get from 3D to 2D. Right? So this Hopf index is exactly the linking number between these 2 pre-images. So in fact, this linking number is the same number no matter which 2 points you choose on this S2. So this is a weird thing. So for example, I can choose as this 4 arbitrary points on this S2. So they all link. Every pair of them link once. So our main result is...
Can I ask you? Yeah, so I think you might have just said it, the very last thing you said, but so is this property of this linking, it's true for any pair of points? So like let's say now
it's true for every pair of points.
Because now I start moving the yellow point around, yellow curve starts shifting.
Right.
Starts evolving, but it always has to stay linked. So it always stays linked to the red.
True. That's true. It's a rather weird.
But then what happens when I take yellow point to the red one?
You just
they just merge together, these 2 loops.
Compressing, this movement is compressing schema.
But they can't merge together because they're linked.
Yeah, so they're very close. So they're
somehow the
they're
point
still linked, but very close, something like this.
So in some sense, red point can never become a yellow point. Is that the statement?
Of course, they are different. Right? So what exactly do you mean?
Well, I mean, there's a point. I suppose, imagine a limit where yellow point approaches the red point.
Yeah, so then this 2D image just getting closer and closer, but still don't touch, of course.
But, so is that true for arbitrary maps?
No, you need to have a Hopf.
That's non-trivial.
Okay, so
that's
non-trivial
one.
map, but that explains it. There's some non-trivial map on
But something happens to that. What's strange is something happens to that map locally. That's what's weird. Like when you do pi 2, non-trivial phi 2, there's nothing, there are no local singularities on the space. But here, there's something singular about space itself.
No, I don't think there's a local similarity. Local is a smooth mapping. Just a
Okay, I don't think there's
Pauli exclusion.
Pauli exclusion.
yeah. So we can type it
Okay,
later.
I mean, it's
I
just.
think I'm
sorry.
running out of time, so let me be quick. So the main result is this kind of Hopf soliton in this topological surface superconductor context. You can show it's a fermion. And this experimental consequence, this anomalous Drossman effect, is a direct consequence of this fermionic Hopf soliton. And we also develop a field theory to describe this unfluctuation. Okay, so how do I visualize this Hopf soliton in terms of this topological surface superconductor? So I can give you a very simple I can realize a Hopf soliton in a topological insulator surface superconductor. So the way I realize it is I create I just have I make a ring of a strong topological insulator. It's a solid ring. And I code the whole surface by superconductivity. And then I create one vortex through this R1 hole and another vortex through the R2 hole. There are one vortex here and another vortex there. So after putting in that two vortices, then you can show that this configuration exactly corresponding to a Hopf texture. So what I mean is, suppose I just choose 2 points on the S2. These 2 points corresponding to the pairing phase equals 0 and pairing phase equals pi. Just pairing, no NZ equals 0. So this 2 pairing phase means the pre-image of this two pairing phase will form 2 different loops on the surface of the superconductor. So every point on the yellow loop have pairing phase equal 0, and every point on the blue loop have pairing phase equal pi. And they are looking weird because these 2 vertices. And because the 2 vertices, you can show these two loops, they link once. And it's once no matter what 2 points you choose. Okay, so I try to say this configuration turned out to be a fermion. And there's
So what prevents a vortex just to shrink and get inside that donut and become just flux? Because vortex has a
that's
line.
exactly the configuration I'm talking about.
No,
So,
vortex has a line tension, so it wants to shrink.
It just face one
so,
to
so the superconductor is only on the surface.
Right.
The superconductor form a torus.
Right, but you have an insulator, beneath the superconducting layer, so my vortex will simply shrink and become a flux inside the donut. So how will you protect the vortex line in the coating?
So by vortex, I simply means that the pairing. Suppose I have this loop, this let's say
I
R2
understand
circle.
what you're saying, but my point is that
How can I shrink?
a vortex is a line singularity, and this line has a line energy.
So where the line is at?
Well, as you draw.
No, this is not a vortex line.
What is it now?
This is the pre-image of the pairing phase. So the vortex is living inside the torus holes.
Oh, it's just a flux trapped in the hole?
Yeah, flux trap in the holes.
Oh, I see.
In this hole and in that hole.
I see. Okay.
So there's 2 vortices. So these 2 loops, they are pre-image of the pairing phase, of a fixed pairing phase. Okay. Okay. So because of pairing, so there only this parity of this fermion number is conserved, and you can show this guy is really a fermion. And there's let me don't go to the technical. It's a more elegant way. The most straightforward way is just to do a numerical calculation. If you do an interpolation between a uniform pairing, which involves no vortices, to a half pairing, meaning there's one vortex here, another vortex there. If I do just an interpolation, you'll find there's a one level crossing, and that one level crossing means the fermion number parity changed once. But because this is a temperature symmetric system, I know the ground state fermion parity is even, so this guy, ground state fermion parity is odd.
But what, I mean, in terms of your experimental setup,
Right.
how do I create, where's this interface? It's somewhere, I have two superconductors, one, you said I have a pairing with a 0 phase and phase pi. Where are those 2 points in your experimental setup? They correspond to what? Sorry, I'm being, you know, you have this superconductor coating your topological insulator.
Right.
What do I do to that superconductor to create yellow and blue point? You know, they,
So these are not. So what you need to create are these two vortices,
right?
and these are just you know, with these two vortices, I can ask for a fixed parent phase.
Oh,
What are the points on this surface have that fixed parent phase?
oh, I see. Uh-huh.
So can I reformulate your vortex analogy, because they're not quite vortices. So you basically create one flux in the hole this way, and also one flux inside
Exactly.
the donut.
Exactly.
So actually you have like,
Exactly.
but those are not quite vortices, but
In the ideal language, it is just phase vertex 0.
right. So you have a spiral.
Okay. So this guy is
Just one remark. So don't hurry up. Let's listen to for the whole story. We are flexible with time. So
Yeah, it's
Yeah.
better to just understand.
yeah, it's
Right.
better to understand. Take your time.
So Ingrid, let me check one thing. So this is exactly same as the P plus IP superconductor having triple topological degeneracy for even number of fermion and no topological degeneracy for odd number of fermion, basically. Am I getting this correct?
So you are saying for P plus superconductor, there's a topological degeneracy for what?
Yeah, if you
So
have
the
even,
P plus superconductor, what do you mean by topological degeneracy?
when you place two-dimensional P plus IP superconductor on torus, you have triple ground state degeneracy when you have odd number of electrons, but you don't have topological degeneracy when you
That's exactly true.
Okay.
I think that's exactly true. This is directly
Yeah.
related to that.
Yeah, okay.
So what he pointed out is there's a sort of known effect. If I have a P plus superconductor, I put on a torus, then I can ask what's the ground state fermion parity. So in fact, I think it's the other way around. So if I have,
Yeah, it's the other way
Yeah.
around, yeah.
so if I have an even number of so I can ask the periodic boundary condition and the anti-periodic boundary condition. What's the ground state fermion parity under these boundary conditions? So what we want to show is if you have a periodic, or periodic, anti-periodic boundary conditions, you always have an even number of fermion ground states.
Yeah.
But if you have both boundary condition anti-periodic, you have odd number of fermion. Okay. So there's an effect, right? So there's a texture. It is fermion. That means it can receive a quasi-particle, so it can absorb a quasi-particle into the texture. Right. So suppose I tunnel an electron into the system. Depending on the energetics, it's possible that this two vortices configuration have a lower energy than the quasi-particle. So in that case, the system want to spontaneously induce such a Hopf texture. So these are the energetics. A quasi-particle leaving on the surface will have a quasi-particle gap, but this Hopf texture, the energy of that is related to the superconducting stiffness by order 1.
So you're saying that if you add one quasi-particle, you can spontaneously
Yeah.
create a magnetic flux?
Yeah, that's what I'm saying. Yeah. So of course this depends on the energetics. So I will need this parent gap to be much larger than stiffness, so that this guy is lower energy. Handle electron, this guy can show up.
But what happens to the quasi-particle in the second case? Suppose the Hopf texture is lower than putting the quasi-particle, than not creating the texture and putting the quasi-particle, paying the gap cost. then what happens in this case? Is somehow the quasi-particle lives on this texture? Or?
Yeah. This is a texture.
Oh, because it's a fermionic texture, so it's like a
Yeah.
state.
So this is a texture.
It corresponds to one fermionic state.
Right. This texture is not like a quasi-particle where you can imagine this electron some leave locally somewhere. But over here, this texture is a global. This is a smooth configuration. So the electron will just leave. Actually, electron just leave in the whole system.
A little bit analogous, like if you have two vortices in the P plus IP, single electron somehow lives between
So it's a smooth texture, so there's no defect.
right. So so in that sense it's different, but in the sense that it's delocalized, just like a P plus IP electron is kind of delocalized between two vortices.
Yeah, I'm not sure. Yeah.
But
So,
can unfortunately, I'm going to ask something which you already explained, but
right, this is
since we
the
have a
first.
limited time, maybe I can ask it again. So I got confused at some points whether this torus represents the actual superconductor or it's an image of something.
Oh, it's the actual superconductor.
So you
So,
imagine.
but the
this
inside
image-
is a torus. There's a solid topological insulator ring.
So you just made a topological insulator into a torus. That's how I should think of it.
No, just a ring, solid ring.
Yeah.
Solid. It's a. Suppose I have a.
Right. So
A
it's-
wire.
The stuff inside
periodic
the
boundary
torus.
condition.
He says that there's a
Periodic
two-dimensional
boundary
thing, which is the
condition.
surface
Good enough.
of the ring.
Yeah, that's true.
This you cut out.
But in
No,
the
there's
real
not kind of
experiment,
inside there.
Yeah.
Is topological bulk topological insulator.
So this is like a topological and made it into a donut?
Yes.
Is it
Yeah.
the idea?
Yes,
I don't want to call it a.
donut.
Oh,
Okay,
yeah,
donut,
yeah,
not
yeah,
torus,
yeah.
but donut.
Just
Yeah,
a ring.
donut. That's
Donut
a
made
donut.
out of topological.
I mean, the donut is the superconductor, and the frosting in the donut is.
Yeah.
No, the donut, no.
The frosting is a superconductor or
Yeah.
the
Yes.
bulk is a
Frosting is a
The
superconductor.
bulk is solid insulator, surface around it.
The surface around it is a superconductor.
That's true.
And then we talk about what does the phase of, well, you didn't have a phase, you had this whole parameter of delta, which was a three-component object.
Right, but on the surface,
Oh, the surface, it lies on the plane.
it
So
lies
it's
on
a
the plane.
two-dimensional
That's a
object.
two-dimensional.
Now let's study how it changes when we go out two loops of the torus. Right?
Yeah. So firstly, so let me explain again what these loops mean. Did that help?
Well, if this is a donut, I can imagine that I go along the loop and I look at this delta, and the delta changes in some way, and you can make a loop.
The point is, if I with this vortex through this hole and another vortex through that hole, I go around some loop on the surface. I find that every point on the surface has the same superconductivity pairing phase. Same phase. So
But that's no vortex.
Like there's no more, before in the very beginning you had, before the donut, you were actually making a vortex on the,
right.
but now you're not doing that.
Yeah, no, not doing that.
There are no vortices on in the superconductor.
True.
All there's now just flux through the bulk topological
Flux through
insulator.
the bulk. On the surface, superconductivity. So in this configuration, everything is smooth. So all the
No,
There are no
there's
vortices
no,
on the surface at all.
No, there's
No,
none.
there's no there's no defect on the surface.
there's
Yeah,
no core
but
singularity.
Isn't
There's no
it also
possibility.
true that you can create a vortex and anti-vortex pair, translate one of them around generate all the way around the donut and pair annihilate them, and that can also give you the same change.
Yeah.
Yeah.
The end state is
Yeah.
exactly have one.
Well, I think
Yeah.
your terminology is confusing because there are not vortices, they're just Meissner screening cards in response to flux which goes this way and flux which goes that way. So you can create them simultaneously and independently. And those are not
I
vortices.
see. So
No, but okay, but can we continue like
Yeah.
Victor's question?
So, but so you said that we have this parameter delta, the real part of delta and the imaginary part of delta. And let's study what happens when we go along the surface of the torus,
right.
along two loops of the torus. And does it wind around or it does not? You said it does not wind around.
So if I go around this simple circle,
Delta one,
delta wind around.
ah,
Okay.
because there's flux inside.
But-
But
Okay.
I can go to a large loop. So this circle wind around both both holes of the torus. So along this whole loop, the face don't wind around. So actually, every point on
the big cycle of the torus, the face does not wind around.
right,
Okay.
right. So you can imagine for a given phase of the pairing, what's a pre-image? What's a pre-image? So what are the points on the surface whose superconductivity pairing have that phase?
I see.
If you keep track of that loop, that will be this yellow loop and the blue loop. They correspond to two different pairing phases. And the link.
They link?
They link once. So they are linked. So I didn't call the
Even though they intersect on the surface, I should think of them as linking.
no, they don't intersect on the surface.
Okay, then I don't understand.
But these loops don't live in the surface.
The loops live on the surface. So all I'm trying to show here is this whole three-dimensional configuration is a Hopf texture. Right? To show it's a Hopf texture, I need to show by definition. So 3D map to a two-sphere. I choose 2 points on the sphere. They're pre-image. There are 2 loops which are linked once. Right? So every point on this loop map to this point, and on another loop to this point. But there's a special case in the current setup.
But the loops are in 3D.
Right.
Loops are actually not just on the surface. They're
But
living in the top
I
right
agree. But in this setup, there's a special. If I choose 2 special points on this S2, suppose I choose so over here there's a z direction is this nz,
Right.
and this xy plane is this parent, right?
Yeah, so somewhere inside there is a point where everything points along on z, and that would be your other loop,
Right.
right? So on
Right.
the surface, you're in the xy plane as far as delta is concerned.
That's true.
Inside there is a loop where everything is along on z.
That's true.
That's this loop.
That's true. It's also linked. You see, right? So this so the pre-image
So the
inside.
image of something pointing up is that loop.
That's true.
And what's the other loop with the image of?
These loops. These are just
around the little loops.
little loops.
So there's a big loop which goes around the hole of the donut, and there's little loop which goes around the donut itself.
Oh, that's not a pre-image. That is
But I
not.
don't know to find 2 loops. So what are the 2 loops?
Okay.
One maps into a point and the other maps into a point.
Right. So this point corresponding to the pairing phase. This is theta. Let's say this pairing is let's write the pairing in this way. So over here theta equals 0. Over here let's say theta equals pi
Okay.
or half pi. So I try to keep track of. I try to ask what's the pre-image in the 3D of the theta equals 0, and what's the pre-image of the in the 3D of the theta equals half pi. So there's 2 loops. Of course, these 2 loops will certainly live on the surface, right? Of the
Yes,
surface.
and they don't intersect.
They don't intersect. These 2 loops are exactly these 2 yellow and blue loops.
Kind of hard to see. Okay, but they don't intersect, right?
They don't intersect.
On the surface, they don't intersect. Okay, okay.
But they link.
They link. Oh,
But that's the paradox.
they link but don't intersect.
Oh, I see. So your entire, when I go, so again, there's a big loop which goes around the hole in the donut, and there's a little loop which goes around the donut itself, right? I just wanted to specify 2 cycles of the torus, big and little. So when I go around the little cycle of the torus, my delta lies in the xy plane, and it goes around
That's right.
just by 2 pi.
Right.
But is that true then that as I go, is this circle is taken around the torus, it rotates, connects to itself?
That's true.
Okay,
That's
now I
exactly
understand.
true. That's
That's
exactly
what-
true.
It's unfortunately blue and yellow lines are hard to
What are
see.
you saying? Can you repeat it?
So there are blue and, well, it looks like a black
Blue
and
and
yellow
yellow.
lines. These are lines of constant superconduction phase on the surface. And these lines, they wind around the handle of the torus and they come back.
How can a line wind?
It's like as if this black little circle, as it moves around the torus, it simultaneously rotates.
Oh.
And it moves around the donuts, and at the same time it rotates by 2 pi. And connects
So,
back
yeah,
to itself,
so
right?
the best thing to interpret is just with a belt. So imagine that this is a constant superkinetic phase. So then you just twist it once around the core and then it joins. So like this. So this is hop.
Yeah, okay, that's
Movie.
kind of
Yeah. So you can twist it like twice. So you create, like if you create a vortex line, a Abrikos vortex, then this
No,
will be
there's
the
no
constant.
Abrikos vortex.
Yeah, good. No, I understand. If you create this vortex, Abrikos vortex, then so this will be constant phase, the edge, and then in that case you twist it and then join the ends, and then they'll give you they'll give you all this helices. But could we can we return to previous slide? Oh,
I'm going backwards.
So this picture on the right tells you that if you create the flux, spontaneous flux in a torus, you lower the energy because your levels are pushed down.
No, what that means is this. So for each fixed pairing configuration, so this axis is a lambda. So when lambda equals 0, I just have a uniform pairing. There's no vortices
Right.
So over here I have, right? So for any lambda, I plot the energy and the values.
So what if I sit at 0.5? So here, if my Fermi level is at 0, I push all my levels down, so I gain in the quasi-particle energy. So that tells you that you can create a spontaneous flux, and that will be an
But this 0.5. So you're saying from here to here?
No, I'm just sitting at delta Hop
Sitting here.
here. So can I create a state with a spontaneous
But
flux?
this state itself is a pretty high energy, right? This state is some weird state.
I understand, but if I just plot the energy levels. Oh, I'm sorry. Okay, forget it. I confused.
So just let's go to the next slide. What does E hop? What does A? So could you explain E? So how do you determine what is A and rho S?
Right. So you can ask what's the energy cost of such a Hopf texture.
What does the parameters have?
So this A is an order 1 parameter. Determined by this ratio of R1 and R2.
So it's like some size parameter, right?
Yeah, it depends on geometry on this R1, R2 size. So the reason is, the energy cost of the order parameter texture is certainly this. So then you're integrating over this two-dimensional torus, right? So there will be this a gradient which also depends on this R1 and R2. So this guy also depends on R1 and R2. So you can imagine that this thing have to have a proportion to rho s times some function of R1 R2 ratio, which is dimensionless.
So to induce superconductivity, you should coat your topological oscillator with some superconductor, which will induce sperming state by proximity effect, right?
Right.
So necessarily, so then if you create phase binding, it induces all the currents in your superconductor.
Right.
Because they're locked because by the Josephson effect. So that would be quite a big contribution to the energy. I'm saying that there should be like integral over 3D, which would extend into.
No, the superconducting phase, superconducting is only happening in the 2D system on the surface.
Yeah, but in the real situation, to induce superconductivity, you by proximity effect. So if I understood correctly, you're inducing superconductivity by proximity effect, right?
Right.
Then you should.
So I'm coating with a very thin layer of superconductor.
You're taking the limit that the superconductor which induce the genuine superconductor which is very thin. So it's the limit of because of because otherwise it will. And then another thing is just another question. So to kill the topology, in this case, it's extremely it's an extremely tiny potential barrier from point of view superconductivity to kill the topology. So it's just condensation energy times coherence length squared on surface. So you just kill in point, you kill superconductivity in a point, and then you can unwind all your Hopf invariants through this point. You just pump in a Hopf invariant in.
You're saying by creating a vortex?
Huh?
Or by creating a vortex?
Or just any kind of point.
Normal.
Yeah, normal point. Normal any kind of point like normal region.
Mm-hmm.
And then this proximity induced superconductivity is very cheap, extremely cheap thing to create just any kind of point like normal region. So do you have any estimates how robust, like energy scale, so how robust it is against this kind of instability? So
Yeah, I think the energy cost of that guy is similar to a vortex, right?
no, much cheaper because vortex is the main. So vortex energy, you create a vortex, you create currents, and here you just should have density singularity only.
Density singularity.
Yeah,
We'll just make delta go to 0 at a point without creating any supercurrents.
You're saying that the energy is essentially finite, right? So it's not macroscopic.
Yeah, it's microscopically small energy needed to kill Hopf invariant because non-trivial topology here has a finite extent in contrast to Abrikos vortex.
So there is no logarithm.
Yeah. There is nothing at infinity, so you create any kind of density. Density 0, no matter how small it is, you can unwind your Hopf texture from this point. And then I wonder if there is any estimate of.
But let me answer this question in a sort of easy way.
Yeah.
So I'm thinking about coating this whole system, the whole surface, coating it by a thin layer of superconductor. So the energy cost of whatever defect you're talking about is mainly dominated by this surface, this a coating layer energetics, right?
Yeah, you say it's very small, right?
Yeah, So that means there's no cheap superconducting hole. This the delta equals 0 part, because if you put delta equals 0, you want the delta equals 0 over the even in the superconducting coating layer.
Yeah, so
that's expensive.
So just to understand this, if I got your point correctly. So are you saying that it should be thin, but at the same time not too thin, so that you have should have significant condensation energy in this genuine
That's what I mean.
No, but he's saying take the 2D superconductor, you drive it normal
in any single
at
point.
any one point. And he's asking or claiming that this will unwind. At one point, just drive it normal. Just heat it up at a point. Not on the whole surface.
The
but just at one point.
then the Hopf invariant is not non-integer.
But just have finite temperature, then by
But
one
the whole-
by
yeah.
entropy argument you will be creating these
understand.
guys.
So this apparent is this is a global texture, right?
Local. Hopf is local.
But then what you need to do is locally you create some. I don't think there's a local way to unwind Hopf texture.
No, that'll be hard because if you have a flux trapped inside the donut which goes like that, even if you make a little hole, by making superconducting normal, the flux is not going to leak out of this.
No, so it's not about the flux. It's
the same thing. You basically create two fluxes which are trapped, and by making a small hole, they're not going to disappear.
Let's discuss later. Let's not.
Yeah. Ian, can I ask you just one question? So you wrote down the Hopf energy in that slide, but doesn't it also depend on whether you're starting out with the 0, 0 flux configuration or a pi 0 flux configuration? Like we are trying to
No,
make.
so this is just the comparing the energy of pairing uniform levelware and a configuration where you have a vortex through each torus hole.
So it's between 0, 0 and pi pi.
Yeah.
Okay,
yeah,
I
yeah,
see.
yeah,
Okay,
yeah.
okay, thanks.
Okay. So in the real experiment, we try to say that there's an alternative approach to avoid this constraint. So even there's a delta smaller than rho s, there's an experiment we can do, which is this Josephson effect, which is exactly related to this Hopf fermion physics. So I don't have to do this tunneling. There's another experiment. So this experiment is a Josephson effect. So this is a Josephson effect. I tune this flux. I measure this currents, tunneling currents on this weak link. So this current will be a function of this flux through this hole of this superconductor. So I'm not say. So this is a general Josephson device. So I'm not reaching this topological insulator business yet. So this general Josephson effect, if you integrate this current over flux, so there's a simple relation that tells you that the state at the 0 flux and state with 1 flux quantum, so this two energy of the system, their difference will be given by the area, the total area of this current. It's simply by this simple electrodynamic relation. So that means if I start from no flux, I end up with 1 flux quanta. So if the system go back to itself, it go back to the ground state, that means this total current, this total area sum over to 0. So you have a period of phi naught. But on the other hand, if your system after turning on 1 flux quanta, it don't go back to the ground state. So suppose it go to some excited states, that means this integration is not non-zero. So to have it go back to the ground state, you will need a larger period. So this is a total integration of the current to be 0.
Well, that's not exactly true because that is true for Josephson energy, but you also have the magnetic energy, the inductance times the flux squared, and that doesn't go to 0. It actually, you tilt the whole sinusoidal curve by just, adding more flux.
Yeah, so over here I didn't consider electrodynamics.
Right.
Infinite lambda.
Yeah, that would give you a tilt of that curve like this. It would go like that.
Okay. Yeah, I guess that's related to, that depend on the
Inductance. Or
yeah,
size of the
the size,
lambda.
the size.
size of the
So
loop.
suppose it's a larger than this weaker. So there's a limit that can go. So with that anomalous Josephson effect in mind, we propose this experiment. So what you'll do is this is a topological insulator ring. I plotted it in the way of a finite length cylinder, but you can also view it as a donut or a ring. So you can tune the flux through this whole phi2, and you can now introduce an extra superconducting loop connecting the top surface and the bottom surface, and you tune the flux through the other loop, phi1. So I try to say, let's coat the superconductor only on the top surface and the bottom surface, and in the middle, the superconductivity is induced by proximity effect. Suppose I do that. Okay. Then, if this phi1 is 0, that means the parent phase here and here are the same. So the logic configuration of a superconductor will have no vortex through the C1 loop. But if I tune the phi1 equal pi, meaning half of a flux quantum. That means the parallel phase on top, bottom, they have opposite side. So the stable configuration will be have a single vortex loop. Sorry, a single vortex through this C1 loop. So by tuning phi1, I can go to the two cases. Either I have a vortex with C1 loop or I don't have. Okay. And with a different value of this phi1, I can exactly do the measurement that I mentioned. I tune the flux through phi2 and I measure the Josephson current of this weak link. And then if there's no flux, I know that no matter what the value of phi2 is, I don't have a Hopf texture. So after I go into 2 pi, I go back to the ground state. So period will be 2 pi. But if I induce a vortex in C1 by the phi1, that means when I tune this phi2, after I go to 2 pi, I exactly create one Hopf texture. And I will change in the ground state fermion parity. That means if I start from an even number of fermion, at 2 pi I don't go back to the ground state. I will go to some excited state with a quasi-particle. So I'm assuming the fermion number is conserved in the system. And that's exactly why this curve will have a period of 4 pi. So this is a sort of a yes or no experiments that one can do. Okay. So there's a field theory to understand this Hopf texture. So what you can do is you have this effective theory of this n, this 3 vector coupled with the fermion, but because this n involves superconductivity, this chi here will be this Majorana fermion. It's just I need the particle hold section of this fermion. So because originally fermion is 4 component, now this chi is an 8 component. Then for any value of n, this whole system is gapped. I can integrate out the fermion. I can get an effective linear signal model of this n. So naively, I will get some dynamical term like this. But we are in 4 space-time dimension.
Can you just went to non-mode basis, basically.
Yeah.
That's all you
Yeah,
need.
that's what I mean. So because I'm in 4 plus 1 dimension, 3 plus 1 dimension, a topological term is allowed because in space-time, 4 space-time dimension, any configuration of n define a mapping from 4 sphere to 2 sphere, and this mapping can be non-trivial, labeled by a Z2 index. So meaning this mapping can either be trivial or non-trivial. But if I put 2 non-trivial together, it's trivial again. So 1 plus 1 is 0. So you allow this term. And this gamma is this topological index of this pi 4. It's either be 0 or 1. So what I will show is, okay, of course, at this moment, you already know that theta can only be 0 or pi. Because 1 plus 1 equals 0. That means theta plus theta have to be 0 mod 2 pi. So it can only be 0 or pi. So what we can show is...
But somehow gamma is written in terms of n hats or not?
Yeah, gamma is the topological index of n hat. So n hat is a space-time configuration. So it's
right, but is there some analytical expression for gamma n hat?
Oh,
Like
good
in the same
question.
way that
I
you have
don't
it for-
think so. I mean, at least I don't know how to write it down.
But
It
is there
certainly
a way to
cannot be-
is there a way to visualize what n hat texture?
Oh, but
Yeah, that's exactly
isn't that
that's that.
Wilczek Z some kind of channel
No, but
size
it-
theorem?
Yeah, I know.
It
So
corresponds to that.
no, that's simple. So the thing is this. I'm sure that this gamma cannot be written down in terms of n itself. So you certainly need some lift. You need to
You need to go to one higher dimension.
One higher
Because and
But
it's
even
fine.
one higher dimension is not enough because So what you are saying is I can represent n by some gauge field, by this CP1, basically.
But I think I was referring to pi 3 of S2. Right?
Yeah.
Talking about pi 4.
Yeah, pi 4 is different. And this Z2 is particularly difficult because you can imagine any integration form
We'll give you the integer.
equal to integer because they add up.
But how is lifting and then projecting? So when you lift, then you get z. You have some representation that gives you z. But how does projecting back to the physical space reduce z to z2? Somehow you say that's the procedure.
Okay, so
Even though here it's not
I sort of can guess what you mean. So usually when people compute this this kind of Z2 index, what people do is this. Because Z2, there's certainly no integration form.
Right.
So what you need to do is you need to embed this S2 into a higher manifold, with a larger manifold, with a higher dimension. And this embedding can have ambiguity.
Mm-hmm.
But after you embed into it, there's an integration form. But because of ambiguity, there are different ways of this embedding. And
That's the z2.
more that ambiguity is Z2. It's usually works this way. Okay. So this is exactly Leo's question. So what's this pi 4 S2 texture in space-time look like? And that texture, you can build it as creating a pair of half skyrmion and anti-skyrmion. Sorry, half soliton and anti-soliton at a given time. And then you rotate one of the soliton by 2 times, after which you annihilate them. So this process is a 3+1D space-time configuration. And this gives you pi 4 S2 equals Z2.
But what is a hop soliton? Is it that texture you've been drawing? That
Yeah,
hops
yeah. Now, this is the hop soliton 1 is the texture I'm drawing, and there's a -1 die, so which is antiparticle.
But it's distributed in space. And it's not like a soliton where it's some distributed set. Well, it's a distributed.
Yeah, it's not a defect.
It's not a
It's
defect.
texture.
Okay.
That's true.
You're drawing it as a defect, but it's really a.
Yeah, that's true. Yeah, so I should make it larger. Yeah, those are textures. So the whole 3+1D space-time configuration is smooth.
And what does it mean? Like when we think of it as if I think of like a Meron, I understand what it means to twist it. What does it mean to twist this distributed? It's becoming difficult to visualize. So there's this extended hop texture, which you're calling hop soliton. What does it mean to twist it? You literally twist it in space, or what?
Yeah, so what I mean is, exactly what I mean is this. So I have as a function of x, y, z, right, and the time. So then what I do is, so this vector,
Really, literally in time, I twist n.
yeah, so it's a space rotation. So what you do is, you have a rotation whose angle depends on time.
Mm-hmm.
As a function of time. So this rotation acting on this x, y, z. So what do we basically thinking about something like this.
Mm-hmm. Well, at every point, I see. There's n at every point, and I
Right.
twist it around. Okay, every n. There's
It's a
an n.
space rotation. So yeah. So for the next time, the configuration compared to the previous time is a
N is
different-
rotated at every point by the same angle.
And now the n is rotated. The coordinate is
Coordinates rotated.
yeah, the space rotation. So suppose I have an n configuration, right?
Right.
Can you imagine I do a small space rotation? Just
But what do I do to n?
just that.
I think it's the same. Right?
Maybe,
I think it's the same.
but in some particular setup configuration of the maybe is the same. Let's say in general it's just a space rotation.
Just to return to experimental setup, so you have a Hopf solid on the torus, right? And how to connect these two. So now we have two Hopf solitons, right? So I started with experimental setup where you had just one soliton prepared on the torus. Physical sample.
This I don't have a physical setup in terms of topological insulator. So this is just a sort of theoretical way to formulate, to understand why Hopf texture is a fermion. And over here I'm just showing a theoretical picture of this pi 4 equal S2 equal 1. It's a non-trivial texture. What that look like? So what I'm saying, what that look like is just this rotation of this solid by 2 pi and move back. Okay, so if this texture lead to a barrier phase of theta, you can simply convince yourself that theta is nothing but the angular momentum of this texture. Right? Because what you really do is just a 2 pi rotation. So if you pick up phase, it's an angular momentum. And if theta equal pi is a fermion, this Hopf texture will be a fermion.
Just to make sure that I understood. So is it correct to visualize this process as the following? So I think I got it.
So basically, it means that in this, this indicates that in this effective theory, I should have a topological term after individual fermion whose theta is pi. So how do I show that? So what I need to show is I write down this effective theory. I integrate out chi. I want to show this barrier phase whose coefficient is pi. So that means I need to show when I tune from a trivial configuration to a non-trivial configuration, there's a phase difference. There's a pick up a barrier phase of pi. But the point is this information from trivial to non-trivial is impossible in S2 because they are topologically distinct. They're not connected by smooth deformation. But that's how I compute this barrier phase. So what I need to do is I need to embed this S2 into a larger manifold so that this deformation is possible. And when this is possible, then I can perturbatively just compute at every step of deformation how much barrier phase I pick up, and I sum them together. I should find pi. So how do I? So the theoretical difficulty is to find a larger manifold, which is convenient in the sense that so you need this pi 4 is 0 and pi 5 somehow contain z such that you have the integration form of the barrier phase. So this is a technical part, but I just want to say that we find such a manifold, which is SU3 over SO3. This is somehow studied previously in energy context. And within this manifold, there's a trivial and non-trivial configuration of S2 can be smoothly connected. So S2 is SU2 over SO2, so there's a natural embedding. And with this embedding and with this manifold, I can do a large mass expansion and write down an analytical form for the total barrier phase in pick up. It turned out to be a 5-dimensional integration. And this V will be some 5-dimensional mapping of a SU3 field. So if I am analytically strong enough, I should be able to integrate do this 5-dimensional integration by hand and show it's a pi. But I'm not that strong enough, so what I do is I just do a numerical Monte Carlo integration, this 5-dimensional integration, and I find it's pi. So I mean, it's some file dimensional integration. So if you are interested, you can try to do it by hand. But there's a simple way, very quick way to do it.
So sorry, this guy integrates either to pi or to 0. Is that what you're saying, or no?
Yeah, so this is a whole integration. So whether that theta is pi or 0 is determined by the integration. The integration should...
That's the coefficient from this gamma.
Yeah, that's the coefficient. This guy is the coefficient of the gamma. And it's a well-defined five-dimensional integration. So this way you can even write down analytically. So there's an example of... So this integration doesn't depend on the details of V. So if you smoothly deform V, this integration don't change. It's topological integration. But there's one known analytical form of V that you can write down. Okay. So that's how we compute this theta equal pi. And this theta equal pi term, I mentioned that it dictates that this Hopf texture is a fermion. Over here, I'm saying that this term also dictates that the surface superconductor vortex, the defect, will host the Majorana fermion bound state. And the reason is I can create a Hopf texture by two surface superconductor vortices. So each one is this is a vortex, this is anti-vortex, or this is hypercloud, this is anti-hypercloud in terms of n. I can pull them apart, then do a 2-high rotation, and then annihilate. So after the whole process, I start from a topological trivial configuration of n and end up with a Hopf texture. So over here, there's some. This is not that common to happen because usually, if you want to create a texture, you need an instanton, a single instanton. But over here, I try to say you can create it with a pair of defects. A pair of defects. Okay. So because from the starting point to the end point, what you actually do is you change the fermion number by 1. But you did it by 2 defects. So that means each defect has to be 1/2 of the fermion. That's exactly why it's a Majorana fermion. And over this process, what you did is this 2-pi rotation will give you a pi phase for one of the Majorana fermion, and when you dilate them together, you go from C to C dagger, and that's why you create a fermion. So this is a conclusion. So there's a single topological term you can write down to summarizing the topological feature of the superconductor, surface superconductivity of topological insulator. And for example, this dictates is fermionic, and this causes the random mode. And there's a anomalous Schwarzman junction experiment is proposed, which is a signature of topological insulator.
So let me ask, so that topological term is there independent of whether you have a vortex or not? Or
Yeah.
it just, in its presence, once you create a vortex, it converts that vortex into a Majorana mode.
And this topological term, we know that it usually changes the nature of phase transition. For example, there's one way to understand this 1D spin 1/2 change. There is there's a gapless phase, and which is connected to this spin dimerized phase, and you can imagine it as a condensation of some instanton, and which carry momentum. So over here, I'm trying to say there's this smooth texture of the superconductor, which carry fermion number, and that also will change the property of superconductivity insulator phase transition. So this is a direction of further investigation. I think that's it. So have another point talk so I don't have time. So if you're interested, you can ask me. So it's about a recent simulation of Howard model. People find a spin phase, which is adjacent to a mode transition, and we have a story about what the phase is.
Maybe we can schedule it at 3:15 today if
Oh.
this is the second part.
Up to your interests. So I don't want to hold you up here. But so let me say I will.
But does it assume that I'll finish on time? That's it. Does it assume that I'll finish on time?
Yeah, but so we will be shifting preliminary. Let's schedule to 3:15.
And we just schedule it for 5.
Oh, so did you?
That's it. That's it.
Great topic.